Hello,
Happy
YouTube.
holidays, YouTube.
Yes, we're
Yes, happy
celebrating
holiday.
the holidays as one should by talking about computer architecture. We're going to talk about functional components of a CPU, the difference between decimal, binary, and hexadecimal. And I guess that's how we start. CPU word is the natural size of a piece of data with which the CPU can interact.
A
And
CPU is a central processing unit. It's the brain of the computer. It's generally composed of the main memory, control unit, and arithmetic logic unit.
oh, that's what the ALU is.
Yes, arithmetic logic unit.
And from how I understand, the CPU is working with these things, right?
Numbers?
Yeah, bytes,
Yes.
right?
The bytes, the bits and bytes.
Well, 8 bits makes
Well, that's how the memory is expressed.
And usually written down in the bit size. This is a 64-bit CPU. Right? Whatever.
That's what it says. Yeah, I would venture to say most of us are using 64-bit computers, though, right?
Yeah, that's what I use.
I think so. How do we know if we're using something more than that?
You would have paid a lot more for it.
Yeah.
Yeah, and then when I download stuff, I only download stuff at 64 bits, so I don't even know. Possibly on this computer I'm talking to you on, because it's a gaming laptop, I probably have more. But my normal work computer, it's 64 max. I know that.
If you right click on your computer and you go into hardware properties, I think it is, it'll tell you. Or actually, if you just go into settings and go to about, it'll tell you what yours is. Mine's a 64.
All right, so the CPU word, I guess, is just this, and it says the size of a natural piece of data with which a CPU can interact. Okay.
So, okay, so this says, excuse me, in computing, a word is a natural unit of data used by a particular processor design. A word is a fixed size piece of data handled as a unit by the instruction set or the hardware of the processor. And most processors these days are 64-bit.
So,
and I would hazard to get, what kind of computer do you have, Ava?
The one that I'm working on is a Windows?
Windows 10?
Yes.
Yeah, so that's 64. Yeah, that's a 64-bit OS, which means it's using a 64-bit processor.
All right. Cool. Then, am I completely incorrect in saying that RAM functions kind of like a hash table or a dictionary? It has things stored with a key reference?
No, not necessarily. I mean, you store arrays in RAM. So yeah. RAM is just the memory that's available while the computer is on, and you lose it when you turn the computer off.
So it's
so that's the difference between like everything's getting loaded into RAM, like your all the applications you're running access the disk or RAM. Your browser accesses RAM. RAM is the main memory of the computer that's not disk, if that makes sense.
It's like you're running memory, like while you're running the computer, that's where things are getting stored unless you're physically storing them onto the hard drive.
Right. But it is like structurally, it's like a dictionary.
No. It says right.
Each shelf has a number. The shelf is an address, and each shelf has bits.
Yeah, so that's like saying here's your address.
Each data type has a different size.
Here's the data. But I mean, it's not correct to say that, because again, this can be an array, right? 1, 10 to 20, whatever, like it's an array. And that can be stored in RAM, and it doesn't have a key.
Okay.
It has
It's just going to be a single value, right, Doc, in each block?
Yeah. Yeah, single value in each block. You can't have like additional values like you can with a dictionary or a hash table.
Okay. So it's just
it's buckets.
Just buckets. Okay. Just randomly assigned buckets.
In Ava terminology, it's buckets.
Okay.
But that doesn't mean that you can't store a dictionary in RAM, because you certainly can.
You can store whatever you want in the bucket. But
yep.
It's a bucket, it's not a dictionary.
Yeah, so you just have a bunch of memory locations, and you can put whatever you want in them. It might be a linked list, or just like you have, of whatever size, right? You have some size of buckets, and this might have a value, and this might have a pointer, and you might allocate this as an array. This is just all your memory, right? And it can have all kinds of stuff in it. Whatever you allocate.
Okay.
So these are more like buckets, right? Does that make sense?
Yes, but
why? And you can have blank spots too.
But why does it have addresses if the addresses aren't the keys?
So you know how when you return a memory address for an object,
and it's a hexadecimal.
Well, that memory location is not a dictionary. It's not a key value pair. It's just an address, right? That address is literally the RAM address for that object.
Okay.
Does that help?
In my brain, it seems like it's still a dictionary. There's an address, and the thing lives and the data lives at the address.
What was the next question? The memory controller?
Yes. So the memory controller directly accesses an address in RAM. And it can jump between addresses 1 and 10,000 exceptionally quickly. So
the main part of this, though, is it is the middleman between your computer's processor and RAM.
Okay. So we have a bunch of buckets that has stuff in them. And then we have a bunch of addresses. And then the memory controller goes back and forth.
So it's like, okay, so you've got a CPU that looks like it looks like a little chip, right?
Right.
And you've got some RAM over here, right? It might be, let's say 1, 2, 3, 4. Let's say it's 4 gig. right? And these are also like little chips, right? And then you have another chip that is your memory controller, and it is, it's like sending instructions between your CPU and your RAM. So it's like a little translator.
Okay.
But it's still a chip. Yeah, this is really what these items deal with are something called
instructions.
Yeah. And you'll, I do believe that, here we go. Jumping to other parts of memory. So there are different kinds of instructions that get sent from the CPU out to memory. And then you've got your little translator here.
You drew your box over it, that last line. It says, like, is that JMP? What's
yeah. Yeah, like jump.
Oh. Oh, okay.
It's literally means jump. Jumping to other parts of memory, like JMP, jump. Add, subtract. Those are all instructions.
We have a chip, and this is our CPU, and then we have the RAM, and it has memory. And we have our little controller here that connects these two.
Yeah, here's a better, I'm going to drop an image into our thread here.
And this thing has the instructions.
It's got everything identified. Main memory here, that's RAM.
Yes, in the big red box.
Outside the big red.
No, outside the big red box. I see it.
Yeah. The CPU has registers that will become important in what we're going to do. We're going to work with some registers. And the computational logic, this is the ALU.
The ALU. Okay.
So then input your code that you're putting in?
Might be. Could be something. Could be some other kind of input.
Like a click or a type or something like how we did for our video game.
Some kind of work, some piece of work that you want the CPU to handle, whether it's you know, your code or an application like Ava was talking about, your browser.
So you put the input into here, it goes into the controller.
Yep.
The controller
routes it
this way to an address that is stored in the ether. And
in the ether? Why do you think it's in the ether? These are all chips.
On a chip.
Yeah, so your RAM is a chip. Have you ever seen the inside of your computer?
Yes.
Yeah, so you know what RAM looks like.
Yes.
It's on a little micro board with some chips.
And then it goes over there, and it's it goes to the address that and grabs the instructions and then does them?
Yes, it executes the instructions.
I think I'm literally just stuck on address and instructions.
Okay, there's not a one-to-one relationship between instructions and address.
The instructions are bytes or sequences of bytes in RAM that a computer knows how to interpret and perform actions based on, which we talked about. Then the CPU is a small a small fixed number of special storage locations built in. There are 16 or 32 of these that have set names, such as R0, R1, R2, and so on.
Okay, so
which is right here.
So again, my strongest recommendation is just like if you were reading a novel and you came across a word you didn't know, what would you do?
Look
Context clues.
You would look it up. And rather, I mean, you know, it's cool to like show people how to look this stuff up.
Right.
But people need to learn to do that.
It's true. From Intel.
Yeah, Wikipedia is actually a really good resource for looking up computer terms as well, because it's usually a verbose explanation. They do a good job.
This part actually made sense to me because it's cycles per second. It goes round and round. That made sense.
Well, yeah, and you hear it, and when you buy a computer, you hear it expressed too, right? In hertz.
Yes. So.
How fast is my computer?
Then the system bus. This is the only question I got right on the quiz because it was a fun word.
What is the system bus?
It's a collection of wires on the motherboard between the CPU, memory, and all peripherals.
What does it do?
It connects the CPU to the RAM.
All right, so the system bus is basically communication between the CPU, the other chips and stuff that are on the motherboard, and which includes your RAM and peripherals. That includes, you know, your hard drive, your CD-ROM drive if you have one of those, your printer. So this is mainly a communications channel. I know it says a collection of wires, which is a weird way of expressing it.
It's like a big flat cable.
It's all about communication. So it's sending bits and bytes across the various chips that are on the motherboard, and controllers that talk to your hard drive, and controller chips that talk to memory, and all that other kind of stuff. It's all about communication. They've broken down to subsystems of the system bus. System bus is all communication, right? The memory controller connects the CPU to RAM, which handles communication between RAM and the CPU. The I/O bus, input-output bus, connects the CPU to, like, your hard drive, right? So whenever you hear about I/O, that's when you're like, you know, either swapping memory out of RAM, or you're saving something to your hard drive. That's the I/O bus. It also communicates with your printer. The control bus allows the CPU to precisely say what it wants to do on the bus: read, write a word, or byte.
The wheels on the bus go round and round.
And the little bus goes round and round. That's right. So this is so these are like subsystems, and this third one is okay. So concurrency and parallelism. Do you guys have a feel for what that is?
That's when things are happening at the same time. Like,
yeah, so concurrency is generally talking about either multi-threading or multiprocessing. And parallelism is something that we won't come across, because that's like a really friggin' super expensive computer that does parallel processing. Well, I don't know, we might, because we have, if you have a machine that has like 8 cores or something, which is becoming more popular, then you can actually do some parallelism, but I doubt that we will.
Well, mine's 6 core. It's close.
Yeah.
So it allows this to do. So I read about the hyper-threading, and then I keep coming across single-thread and multi-thread operations when I'm reading about doing back-end things. And because that's a concept that, it's a vocabulary word that we use, but we don't actually, like, go into the thing?
That's a Google thing. So and there's something unique to Python about this too, right? So especially when you're talking about multi-threading. Multi-threading is actually not the recommended, if you want to do concurrency in Python, multiprocessing is the best practice. Multi-threading is not. And the reason for that is the way that there's a special mechanism in the Python interpreter called the GIL, which is a locking mechanism. And you either have to like go into the interpreter and turn that thing off, which is not something you want to like, do. You don't really want to go around and muck around in the interpreter unless you're like really familiar with the source code of the interpreter. And you're ready to like start customizing the Python interpreter. So multiprocessing is the preferred way for concurrency in Python. But if somebody says it to you in the work context, you want to know what it is they're saying.
Yeah.
Yep.
That's all. So concurrency is something that you probably will run into, especially if you're into microservices or if you're into some types of backend work.
Yeah.
So you should definitely know what concurrency is.
Yes.
And you should definitely know that with Python, multi-processing is preferred over multi-threading.
Yep.
I have no idea what that means, so I don't do backend.
Google, write all that stuff down, write all those words down, just like if you were reading a book, a novel, and you came across a bunch of words that you didn't know, you would look them up.
Well, see, whenever you're on doc, I always have my sticky notepad out so I can write down notes.
Oh, okay, cool. So sticky note says, you see a word you don't know, Google it.
Mm-hmm. I
Always.
still got a bunch left over from, I think, the last time that, when we were doing the stacks, that's what it was.
Yeah, and you should always start with definition. So concurrency definition, or whatever it is, definition, and then you can move on from there to learn, more about it. But you don't want to just look up concurrency because God knows what kind of results you'll get.
I just want to see a little code snip. It'll make sense if I see a code snip.
You know it won't.
It'll make more sense if I see a code snip. I see a bunch of words and I'm just like, oh God, I've got to look up all.
Google has all of that, Ava. Google has
of these words.
Google is your savior. Oh, it's the challenge.
Yes.
How long does it take the number of transistors on a CPU to double? How long does it take the number of transistors on a CPU to double? What is the common name for this rule of thumb? Moore's law? I don't know. Why are registers necessary?
Oh.
Yep.
Yeah, it is
Moore's law.
Every 18 months. I remember reading about this one.
Yeah, we're beyond that now, though. I think we've surpassed Moore's law.
Yes, we've surpassed Moore's law, and I think we're closing in on the singularity.
So they say. Why are registers necessary?
The register is the storage of the address, and the RAM is the information.
Nope.
No, did I get it backwards?
Nope, none of the above. Look up CPU registers defined, or on Wikipedia, one of the two.
Oh, I don't need that here. It's a quickly accessible location available to a computer's processor. That is not
RAM is outside the processor.
Yeah, that's not what I said. I thought that's what I said.
No.
That the register was the address and the RAM was the stuff.
That's not correct, though, because the register is actually holding data.
Okay, so the register is not the address.
Go back to your...
quickly accessible location. It's the location. The location's not the address.
No, it's like, so a processor register is a quickly accessible location available to the computer's processor. Registers usually consist of a small amount of fast storage.
Oh, that's the
data.
RO, R1, R2.
Yeah.
And it's slightly faster than RAM, and it doesn't disappear.
It's way smaller, right? So it's just trying to hold specific instructions for the CPU, and RAM holds all kinds of data, right? Not just instructions for the CPU.
So this is fast and specific. And
it's inside the CPU.
Okay.
RAM is outside the CPU.
And we don't use RAM because RAM is outside the CPU, and this is inside the CPU.
Yeah, RAM is more than what you need for. Well, when we work through these problems, this will probably become more clear how you use registers and what they're for.
Okay. Cache is useful because it's faster.
What's a CPU word?
That's like the 8, 16, 32, not 28, 32, 64, 128 that like tells you about the bit size that the CPU works with.
How many bits are in a word?
8 bits.
That's it. That's one way to describe it. That's one word. Yes. That's one type of word. You might have a 64-bit word too, though, right?
Yes.
What is the system bus and how wide is it?
It depends on the computer. I've seen them this wide.
It's a wide bus. What is a system bus, though?
It is the thing that has, it's the collection of wires that carries the instructions to and from locations.
I like it. And how wide is it?
It's wide. I don't understand that question.
This is expressed in hertz.
Oh, okay. Oh no. How wide is the system bus?
No, how wide is the bus? Not the system, the bus.
An MCU is either 8, 16, 32, or 64. Although the Marvel Cinematic Universe of just a 4-bit data bus or greater, 64-bit width are possible.
The Marvel what?
The Marvel Cinematic Universe, the MCU.
The width of the address bus determines the amount of memory a system can address. For example, a system with 32-bit address bus can stop scrolling, can address 2 to the 32, ...
Oh, okay. I couldn't see it because your face was over
System RAM, of course, is not an accurate, that doesn't have anything to do with what... Oh, let's watch this video for 2 minutes and 28 seconds.
All right.
Welcome to LearnComputerScienceOnline.com, and in this video, we are going to discuss computer system bus width. The computer system consists of number of internal and external components. These components are physically interconnected and communicate with each other through a network of wires running across the computer system. These wires connecting the internal components are referred as computer buses. The computer bus is unessential to the functioning of the computer system. The size of a bus can be measured in terms of its bus width. The bus width is an important performance parameter because it determines how much data in terms of bits can be transmitted at one time. The larger system bus width, more data will be transferred, which significantly improves the microprocessor performance. Let us consider one example. A 64-bit computer bus has 64 parallel cables, and therefore it can transmit 64 bits of data at a time. Whereas a 32-bit bus has 32 wires, and therefore it can transmit 32 bits of data at a time. We can compare the computer bus width with the number of lanes available on the highway. the road with more number of lanes can carry more volume of traffic. Similarly, a computer with a higher number of buses can carry more data for increased performance. Let us now summarize the computer bus width as number of bits transmitted in single operation. In other words, larger the bus width, better will be the computer's processor performance. That brings to the end of this tutorial on what is a computer bus width. Please visit our website www.learncomputerscienceonline.com to learn computer science online. If you have liked this video, please give us a thumbs up and consider subscribing to this channel. Thanks for watching, and I will see you soon with another computer science tutorial.
Okay, you can kill it.
Nope, you have to listen to the outro.
It was jamming out.
Hey,
over
look, there was a bus. Oh, wait. Scroll down to where it had the wires again. Can you just click on that?
Yeah,
I don't know. On the little scribe thing here.
Okay.
Too far.
No.
Go back.
More back.
Yep, right there. Where'd it go? I saw it.
Me too.
There it is. These are the ones that you most commonly see with these ribbon cables.
Yeah, that's what I was talking about. The real wide ones.
Yeah. I mean, obviously.
Oh, that's the one that got broke on my husband's computer.
Yeah. And these are going out to like external devices.
I leave the hardware up to my husband.
Describe the pins that are on a CPU chip. Somebody said they look like SpongeBob.
That one was not me for once. They're pointy.
Yeah, okay. Google. Hello, Google.
Wait, no, I'm not done. They're pointy, and it's they're equal in number, right? Because of RAM and bits. That's not the word I was looking for. Am I correct?
But how many pointies are on there?
There should be multiples of 4 because of 4. Yes? It seems like it should be the thing. Describe the pins on a CPU. They're pointy and they're equal, right? They fit into a socket of the motherboard. They form an electrical connection, and they fit into the socket.
Well, all I know is they got little holes on there, and then you got to solder them in, and then they connect to something on the motherboard. Look at images.
It just said describe them.
Well, I'm a visual person, so it's easier for me to describe something if I can see it.
I'm over here yelling and screaming on mute.
Yeah, they're just like, oh man, Doc's being extra mean to us. She's just making us guess and watching us cry.
Go back to where you were. Go back to where you were. Yeah. Scroll down. Wait, stop. What are all those pins for?
Oh, this is down here.
They're for colors.
No.
2 for memory data, 1 for other memory related signals, 1 for power, and 1 for the cpu bus.
cpu bus?
And that one is mostly reserved.
Is that reserved for the QPs?
The cpu bus.
Okay. Google says QP bus is what? Quick path interconnect.
The cpu bus. Okay. So, as a point-to-point processor developed by Intel, which replaced the front side bus.
Too many buses.
Which is like a side bush.
Okay.
Side. What is a CPU instruction?
It's the program. The
What
direction.
program?
Any of them. That's related to the address. Like stop, start, go, print.
Read, write, jump.
It's in base 2 because there's a 0 and a 1, and they're logical. Basically, they can also be logical operators of yes, if true and false. On and off.
Yes, they can be logical operators because on is truthy and off is falsy.
Yes.
But which one is which?
Whichever one it makes your head happy to think with.
On is true and off is false.
Yes. It's base 2 because it's 0 and 1.
Which one is false? 0 or 1?
0 is false, 1 is true. Yes.
Are you sure?
Here.
Is it?
Look in your chat and play that.
Oh no.
It's only 3 minutes.
Because it is.
Perhaps we could get, say, 2 volunteers. Come on. Okay, so one hand here and one hand over here. Come on down if you want to meet me on either end of the stage. Come on over here. Come on down. What's your name? Priyanka. Priyanka. Nice to meet you. David, come on over. And stay, if you want to wait right here. And what's your name? Calvin. Yeah. David, nice to meet you. Come on over here where Priyanka is. So Priyanka, you raised your hand first, so you get to choose. Do you want to go first or second in this little challenge ahead?
I'll go first.
OK, so Priyanka is going to go first. If you want to stand over there, Calvin. So the challenge ahead here is, could you go ahead and represent for us in binary using each of these light bulbs and in turn switches as 0s and 1s, say the number 50. So you might turn one light bulb on representing the 32's place. Might turn a light bulb on representing the 8's place. So our total count now is 32 plus, not 8, plus 16, I think, which is going to give us 32 plus 16, which is 48. And so we get now a round of applause, if we could, to Priyanka. Thanks very much. Give us just a moment. So each of these light bulbs then represents just a switch or a bit. And inside of your computer, if you've ever heard the phrase transistor, a transistor is just a tiny little switch. And our computers today have millions or billions of these switches that they use physically to represent information and store values, just like Priyanka did here. So if a computer were to represent the number 50, it would literally turn on 3 switches of sorts, store a little bit of electricity here, here, and here to represent the number 50, and it would leave off all of the other switches, the other 5 in this case if we're using 8 bits or 1 byte. Calvin, you raised your hand second, and so we have one other challenge ahead. Fortunately, these things are magnetic, so let's take things up a notch. And if you would, Calvin, how about the number 13, if you will? How would a computer represent the number 13 where each of these light bulbs from 1 to 128 represents a bit? We had, of course, the 1's place over here, the 2's place, 4, 8, 16, and so forth. So we can ask the audience, should we turn on, for instance, this bulb here? No, way too big. How about this one?
No, too big.
OK, and you're in charge. Ask the audience.
This one? Yeah.
OK, so we have 1, 2, 4, 8. 4 gives us 8 plus 4 is 12. And another round of applause if we could. Thank you. You got the tougher job. Thanks to you both.
A to F makes sense. But A, B, C, D, E, F. Cool. And F and C is 12. Because we have gone beyond 0 to 9. So it becomes C for some reason. And that works.
for some reason.
Yes.
A is 10, B is 11, and C is 12.
Yes. I got there. This part of 0 of 11 being no, 11 is 11. This part of 1100 being 12 is not okay.
But you have to have all those zeros too.
Octal is base 8. So if I'm understanding, base 8 goes 0 to 7? Yeah, 0 to 7. Doc, I think you're muted again.
What?
Okay, so base 8 is Linux. Unix goes from 0 to 7, right?
Yeah, that's correct.
Well, Unix, isn't that Linux based?
It's the other way around.
Linux is Unix based.
Oh, okay. That's what I meant.
Yeah.
That's the same way, like when you think about gigabytes and kilobytes, that all it is it's 1024. Kilobytes is 1024 bytes. And
these are powers of 2.
Huh?
These are literally powers of 2.
Yeah.
So 2 to the 0, 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8, 2 to the 4 is 16, 2 to the 5 is 32, etc., etc.
It's just doubling itself.
Yep.
Oh, okay.
Yep.
But that's not how you want to think about it. You don't want to think about it doubling. What you want to think about it is being powers of 2. So if you say, like, you should know that that 2 to the 4th is what? What is 2 to the 4th?
8.
Nope.
Oh wait.
Wait, no, 2
to the 4th.
Oh, 2 to the
16.
4th.
16.
Correct.
I like how she highlighted that part.
Oh, okay. Let me show you. This is cool.
I get it. It just takes way too long for me to wrap my brain around everything. It's so beautiful. Look. So let me explain this part, right?
It's Jello. Okay, go ahead. Explain.
I can explain this. Okay, so this is how you declare a variable that you can reassign later. You can't reassign if it's const. A let can be reassigned.
So in other words, it's like a list.
No, this is a variable. A let is just you'd be like, okay, let it, like in Python you can reassign the value of any variable you've got. You can like reuse it. So let can be reused. There's another one called const. CONST. Once you assign const, you can never change it. So if you have const binary and then you assign it to binary of 101, if you write a function that wants to update your binary, you won't be able to do it because this is a constant. This is there forever.
Unless you delete it.
Yeah, unless you physically manually remove that line from your code.
Oh, okay.
Let. Yeah. Okay.
Let allows you to update this. So if I declare my binary with a let, and so this has got a temporary value of OB101, and then I write something that updates the binary, I'll be using a let. So generally speaking, a const you use globally, a let you use locally.
So in other words, you don't want a const if you're using a pointer to point to it and you want to change it.
Yes, exactly.
Okay. Yeah, don't pollute your mind with this stuff, Joanne. You're stick with Python. You'll be in good shape.
So this is how we convert it to a number. So it is somewhat, JavaScript is a typed language, but not very strongly. You can change it to a number, and it'll spit out 11 as a number. And you can parse int from the string of 101, and then you use base 2 here, and then it'll also send out a number of 11. Isn't that cool?
Awesome.
Yeah.
It's gross.
Look at it, Doc. Look at it.
Gross.
Look at it.
I'm going to leave in a minute.
This is my minor revenge.
More JavaScript. There's your const.
Yeah. So this one you don't change, right? Decimal.
Okay, I'm going to go and start binge watching The Undoing because that would be better.
Oh, come on,
So
dog.
that's how you interpolate it into stuff. Come on, this is like an F string.
What?
Hey, wait a minute, Doc. Didn't you learn Java first?
I did learn Java.
This JavaScript. There's a difference.
This is like trying to hold Jello.
JavaScript is kind. Java is not.
JavaScript is all over the place. It's loosey goosey.
It is. Yes, that's why it's kind. Java makes you like be intentional.
It also allows you to make many errors.
Yes.
So
that's
then
why
Java is closer to C?
What is?
Java.
No, Java is pure object-oriented.
Yep. Everything's
an object.
Everything forever.
Everything. And it's also statically typed. So it's very easy to do type checking, which is hugely helpful when you want to like avoid runtime errors.
Yep.
And JavaScript doesn't do that. It has runtime errors all over the place.
Forever. And that's why that's why in web a lot of people are switching over to TypeScript on the front end.
Yep.
I get in trouble every time I explain it this way. I should come up with a better way of explaining it. But it's basically it's more Java-y JavaScript. It's very strongly typed, and it forces you to pass. You can't pass props if you don't declare the type, and it keeps things a lot more streamlined.
Yeah. It's definitely more JavaScript, but it does enforce types, and that's a good thing. That's a very good thing.
There is almost no learning curve, except for having to type that except for all of your parameters have to be typed.
And if you do type hinting in Python, you have to do the same thing. So, and you definitely have to do it in Java. Everything is statically typed. So, if you don't declare it, you get a type error.
I started teaching myself some Java, and
it's really the best. If you want to thoroughly understand OOP, it's the language that you need to do it with.
It's kind of like on my back burner on my list of things to do.
Yes, Python gets close, but it doesn't enforce. I think it enforces 3 out of the 4 requirements for OOP.
But
so
there's a built-in function that'll do it for you.
Well, that's not the point, though. You have to do it by hand so that you understand it.
Okay, so you have a whole bunch of zeros. And this is like counting if you only had 2 fingers, or if you wanted to count with way more to higher numbers and use only the 4 fingers that were not your thumb. So this is your 1's place, your 2's place, your 4's place, your 8's place, your 16's place if you want to go to your other hand now, because we're just going to do 2 at the same time.
Okay, stand by. Now, what do these have in common with the stuff we were talking about before? They're all powers of 2.
Yes, your 32's place, your 64's place. I'm still trying to get to 128. Well, I remember the number exists. And your 128's place.
See that? You're doing good.
This is how he would count if God hated us all. So the number 3, so these can only flick to 0 and 1.
Flick?
Flick, yes.
Light bulbs.
You want me to explain it? They're flicking. We turn 0 goes to 1, 1, and it goes away because now we're on 2.
No, it doesn't go away. If you want 3, it's just a 1 and a.
We're on 2. Now we're on 3. The zeros are always there for right now because I don't.
Oh, so you're trying to count 1, 2, 3, 4 like that?
Yeah.
Okay, but these zeros stay.
Yes.
So it's not just the 1.
This is the flicking side. This is 5.
I'm not even going to talk about what other things get flicked, but okay.
Gonna make me cry all over again. 6, 7, and we go to 8, and this does not become a 2. Moves over here. That's goes back to being a 0.
So that's 12.
This is 12.
That's 13.
Yep. I lost count.
Next is 14. Next is 15. Yep. Next is 16. You're doing great.
They're the zeros that aren't there because it's a lot of drawing and undrawing. And if
I'm just saying that for the audience at home.
And if we are
17.
Yeah. And if you're gonna do a larger number, oh god, if we're gonna do a larger number, like 65, you can take these numbers here is what you're subtracting. We know that 65 is less than 128, so we're not going to use that. But hey, 64 is, we can't use 32. We subtract 64, so we can turn on 64. And then there's 1 left over, and turn on the 1. So 64 be 1, 0, 0, 0, 0, 0.
I dual?
Huh? Oh.
I dual?
Yep. Ones and zeros.
Dual. So there you've got a 1 at one end and a 1 at the other end and a bunch of zeros in the middle.
Now, in binary, if you are on an 8-bit system or 8-byte system, then you would still have all those zeros in place, right? All the way up. Or just...
How big is your word on an 8-byte system? 8-bit system, I should say.
Well, yeah, that would only be 8 bits.
Right. So you wouldn't have those others.
Right.
You wouldn't have those bigger numbers.
So, yeah, that's kind of also where I got confused. So we can't store a number on an 8-bit system that's larger than whatever can be held here.
Yeah. That's why that's why people are glad when they get a 64-bit computer instead of a 32-bit computer, because it's going to be faster. So you'd end up swapping them out is what you'd end up doing, right? You have an 8-bit word, and you would, if your 8 bits are filled up, then you'd need another 8 bits to allocate.
So if I have whatever this is, and I need to store it again, it gets overwritten, or it gets stored at the same thing, or am I just thinking of this wrong?
It depends on how the memory is allocated. I doubt that it would be overwritten, but it usually, when you're handling memory, what you do is deallocate the memory and grab a new bit of memory. Once it's deallocated, then you can overwrite it. But you usually don't do those steps like together.
Okay.
You see what I'm saying?
So it's already been allocated and it's storing this, but now it has to store something else. So it just says, so it keeps it there.
It deallocates it.
So it says no more of you. It's
still there, but it's not addressable.
Right.
Yeah, if you don't have anything and
so basically it just erases. So in terms of our linked list, it just makes these pointers point at none, and so it's deallocated. It doesn't remove it. It just says you're not pointing at anything.
Yeah. And then it says that, okay, computer, you can overwrite this later on.
Yeah.
Yeah, now allocate me some new memory.
Yeah, that makes sense. So for some reason we also have hex, and all of this, and we don't even use it in the project.
Say it again.
So all of this with binary and hex, and they don't even touch it in the project. They give you the binary already. You don't even have to convert it yourself.
Yeah, but you want to be able to. Okay, so they give you this novel. They don't tell you what all the words mean, but they give you the novel to read.
It's a terrible novel. I want my money back. There's no words, only numbers. Worst book ever.
No. They give you all the words. They just don't tell you what they mean.
So you switch them into 4 bits. For reasons I'm really not entirely certain, we've got a bunch of stuff. Series of 1s and 0s. And
I like the fact that you're soldiering through.
Got to get through it somehow.
Yeah.
Well, you could always have Doc explain it all out.
If I don't learn by reading or listening, I have to do it.
That's how I am.
And it's really helpful to have somebody who knows what you're doing. Otherwise, you're just like, well, I did it, and I'm not really sure how, but observe this building.
Yeah.
It works. I'm not sure what I did.
Because it is.
Because it is. I mean, I can take all of this on faith that it works and be fine. But that's not going to get me that $1 million a year job that I want.
No.
But for reasons, this is 3. So we already explained that 11 equals 3. So
I can't even do it as strongly as you do. You have better breath control, probably.
I do. You also have to feel it in your soul, Doc.
Okay. And I don't have one of those, so.
Nope. So we have explained that because of counting in base 2, 11 equals 3. But what happens when we should realistically count to 1200?
You mean 1100?
No, this has got to go higher. It's going to be 12. Too high. It goes to C. We got too high. Counted to 10. Now we're going into letters. So we got to 9, 0 to 9. We got up there. And now we just go over to letters. A equals 10. B is 11 in decimal, not in binary. And C is 12. Or in this really strange system, 1100 B. Oh, shit. Yeah.
Did you strain something? That's not the noise you made. It sounded like you strained something, like you pulled a muscle.
In my brain. So there we go. 1000, 10, or A. And then we use this to write colors in CSS. I'm not actually sure why on that, but it's one of the options that we have available. 1, 2, 4, 8, 16. Okay. This is 16, 8, 4, 2, 1.
There you go.
10, 7, 27, 1, 2, 4. So this is 7.
So that one's going to be 128 all the way at the left.
8.
And then you go to 64. And then 32.
It's not how they 30, right? 2. Okay. Let's make it 10 and a 4. Then we make a 10 and a 2. Oh, that doesn't make any sense. 224.
224 plus 7. And then they're wanting it in hex.
24. Hang on. 24. 27. 7. 1. 3. 231.
Yeah. And then they want you to convert that to hex.
Yes. 1, 0, 0, 1, 1, 1. And if we go back up and we look right here, okay. This one is a 3, and this one is 12. So it becomes OX3C. So this is not 3. This is only going to 8. It's split in the middle. So this is 1, 2, 4, 8. 8 plus this is 12.
And that would be 2.
14. So this is 14, and 14 is A, B, C, D. So this
No.
is, yes. 10 is A.
It's 12.
Huh?
C is 12.
Well, wait. Is this 12? This isn't 12.
That's
This is
14. But C is 12. So it would be E.
C, D, E.
You got this, Ava. You got this.
I keep telling y'all I can't do math. Let's prove my point. So 100. Okay. So
111 you
1,
just did. So what was
3,
that?
3, 4, 7.
Yeah.
So 7 is less than 9. So this is OXE7.
See?
I see, I told you we'd still be doing it when Doc came back to give from dinner talk. And 27 in binary, 27 is more than 32. So 27 less 16 is 11. So not 30, so it's 32. This is 16, 8. 3, 4, 2, 1.
There you go.
See, with practice, you got it down, kiddo.
Yep.
And write a computer program that outputs a value in binary. No.
She said no.
No, this is beyond the scope of what I'm of.
Well, you have to leave something for the audience to practice on their own.
Yeah, y'all do this for homework. Okay, so as we discussed earlier, memory is a bunch of buckets. And because we selected in the README 256, we create when we initialize our CPU class, we are initializing our memory that's got a bunch of buckets with a value of 0. So 256 of them to be precise.
Is there a reason for the 256?
The README says so.
Okay, just because.
Yes. Our the PC is initialized at 0. That's basically our pointer, for better or for worse. We'll be increasing and decreasing that in and this is finding our locations of the pointer. Our flag, when we've built other programs, we've created a flag that's true, false, or yes, no, or whatever. This is a binary flag that we either raise or ignore that lets us know when something is running. I forget what IR is. Husband, what was IR again?
IR?
Yes.
Internal registry.
The internal registry. This is why I thought everything was a dictionary, Doc. The internal registry is a dictionary. Their key and our value. Our self registry is another series of buckets. But we only have 8 of them. Self.stopped is false because our CPU is running. So if stopped is false. If stopped is true, then something broke and it will stop. It's basically another flag. And I forgot what SP was, husband.
something pointer?
oh, never mind. I lied. This is the pointer. So this is our current pointer. These are all of our hard-coded values that we will have to implement eventually. I just hard-coded them all in there because I was already doing it, and I didn't want to do it again.
Yeah.
So
What is all the... Okay, well, I understand pop and push, but...
these are all of the functions that we'll be building this week.
Okay.
And the README has all of these binary codes that are attached to it. They are also down here in the program. They've been hard-coded in here. There's a stretch goal to basically create a dictionary and code them up over here. HLT is halt. So when we want to create halt, it basically means to exit the program. So sys.exit.
See, that's a lot more coding than you think.
The setup took a minute, but if I hadn't been so dumb at math, this wouldn't have taken that long to ignore this section here.
Oh dear God.
You're not dumb at math.
Less good than I want to be. So we had our it would have only been this section here and these three functions.
Oh, okay, because I was going to say none of the other stuff is there.
Yeah, no. The other stuff is for stretch goals and things.
Oh, okay.
Halt is to stop. It's to completely stop our computer. So we're using our system. At the very top, they very helpfully imported system for us. So system.exit exits the thing that we are exits. Yeah, it exits our computer. It completely stops it.
Or the program.
Yep. And if we go into our, so we have all of this information is in our is in all of these readmes. There are so many readmes. If you are following along, do take the time to read the readmes. We're not going to read them to you or for you. We're just kind of, I guess, here so you can check your answers. Hey, bud. Yeah. See, as I was saying, these codes are already here. We have call, return, jump. We have all of these codes in our operations. Add, subtract, multiply, divide, modify, increase, or increment, decrement, increase, decrease, and not or. So all of these were already there. So that's all that these binary codes are up here. That's where we got them from. That's all. So this is the part that looks complicated, but it's actually easy.
So you didn't actually have to do the binary on that then. It was already done for you.
It was already done for us. That's why, yeah. You should practice and understand it, but for the purposes of the project, they actually already did it for you. There was no complicated part there. It was already there. And that program, again, is down in here when it has the load a program into memory. You don't know what the address is. There's hard-coded the program. And for the instruction, like this all comes with it. The only thing that we have to do is create a read, a write, and a read and a write. And we have, see, I was prepared to explain this part, and then it's all over in here. So it is all in here. So these are our registries. The MAR is the address. It's not really the address. This is how we read what's there. This is our RAM read that we have to write.
Was that clearly done where they just made it RAM backwards?
Huh? Oh, MAR?
Memory. Oh shoot. Memory allocation. I can't remember what the R is for. Read? Memory out? No. And our write is just assigning our value, right? So our self.registry MAR, we give it whatever we have passed in as our MDR.
Okay.
Does that part make sense?
I think so.
Cool. And our 3 bits here. So we already covered halt is stop. We exit the program. Shoot, LDF.
Memory address register.
Thank you.
You're welcome.
LDI.
It says LDI load immediate, store a value in a registry, or set this registry.
So takes our registry at our memory location of wherever we're currently at, +1. And then we just kind of shift it 1 over. That's pretty much it. That's all we're doing. And when we print has the instructions at print. And so if we were to print where it currently is at print registry self.pc, where our current address, it would print the print in an infinite loop. So we have to go to PC +1. So it will print the thing that it's supposed to print instead of printing the instructions to print.
Okay.